I'm Bob Duhamel, and I'm going to explain the wave-particle duality of light. Now, the wave-particle duality of light means that if you observe light and expect it to act like a wave, it acts like a wave. But if you observe it and expect it to act like a particle, it acts like a particle. How can this be? Well, there are some very good videos on the internet that have much better graphics than I can provide that I have linked in my description below, and I highly recommend those. But they fall short in part of their explanation. They leave too many questions, and I'm going to complete those concepts and answer those questions. To begin with, how do we know that light acts like a wave, or that it acts like a particle? Well, we can only know this by observing what light does and seeing how it acts. So, how do we know that light is a wave? Let's take a look at one thing that waves do. This is one way we know. Let's take a look at some waves in a pond, and we'll make a wall in that pond with a couple of openings in it. And we have some waves coming at that wall, and when they hit the wall, some of that wave energy will go through those holes and start to radiate out in a circular pattern from each hole. And here, these lines are where two wave crests. So here's a wave that goes down and up. Here's a crest, and here's a trough. The lines represent the crests. The point halfway between the lines represents a trough. And where two crests come together, we will find that the energy combines to make a crest that's twice as big. So we'll have huge crests here, 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 and here, wherever two crests line up. And in places where two troughs line up, like here and here and here, we will get a doubling of the trough. So if two troughs come together, we will get a deeper trough. So along a line, you'll see that there's almost a straight line here, not very well drawn, but you can see it in other illustrations that it's a fairly straight line, maybe curving a bit. We will get a line of crests, and they will radiate out in a pattern such as this, and in between lines of deep troughs. So we get an interference pattern between these two sets of waves that has crests, troughs, crests, troughs, crest, troughs, crest, trough, crest. And so we get that pattern that we can see as the waves go on. And if we do the same thing with light, when we call this a double slit experiment for this reason, let's make a cardboard or metal wall and put two very close together slits. Two tiny slits very close together. So we have the same thing. We have a wall and a place for the energy to go through. Let's look at this from the top. There's one slit, there's the other slit, and if we shoot a beam of light at it, we get an interference pattern on whatever we have over here. So just as when surface waves on a pond goes through a double slit, we get an interference pattern, light does exactly the same thing. So light must be a wave. But let's look at light from another point of view. Let's say you're an astronomer and you're measuring light coming from a distant star. And we have some way of detecting that light. One way that used to be done was we would use a photodetector that used a metal called selenium. So we'd have a selenium plate and a little rod. The plate would be negatively charged, the rod would be positively charged. And when light hits that plate, it energizes electrons in the selenium. They kick off and become free to move, and because of this positive charge, they will move to that post, and so we get an electrical current. The more light coming from the star, the more electrical current. But let's say we're measuring a very faint star. And we find that the light hitting the selenium plate does not cause a steady current, but every once in a while we get a single electron to move from the selenium plate to the post. And so what it appears to be, is that a certain amount of energy comes from here, hits the selenium plate, kicks off an electron, and makes it move. So it appears that if we get a small enough amount of light, little packets of energy are coming and causing something to happen. So something started here, traveled to here, and made something happen. So light acts like a particle because that something that happens is a certain packet of energy. So we call that little packet of light a photon. So light acts like a wave if we treat it like a wave, but we can also see that light acts like a particle. Now that we know this, let's take even another look. Let's have a wall of photodetectors. This could be anything from silver iodide crystals, such as in photographic film, or it could be p-n junctions and little diodes, or it could be the cones or rods in our eye, but let's just make a wall of detectors and shoot a beam of light at it. And what we see is that those detectors detect the light, and let's say this was a piece of photographic film, it would just be exposed and it would just turn dark when being developed, which is what a negative would do. But let's cut back the amount of light. Just keep cutting it back and keep cutting it back, and we'll find that as we shoot this beam of light at that wall of detectors, that we start seeing a reaction here, and then a reaction here, and then a reaction here. We start seeing reactions all in random areas on that photodetector. So what we see appears to be particles of light, one hitting here, another hitting here, another hitting here, and they hit at random places. So if we throttle back that light enough, once again it starts to appear as though it is particles. And we call those particles, once again, photons. Now let's put that double slit here again. And clean up our little photodetector and shoot a beam of light at it. And what do we get? We get the waves coming through in the interference pattern, as we talked about before. So we get a concentration of light here, 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 and here as we get that interference pattern. So it acts like a wave. But let's throttle that back and put less and less light until we have individual photons coming here. And see what happens. Well, with individual photons, here's what we would expect. We expect that one photon may hit here and not go through the slit. Okay, that's not part of the experiment. But let's say a photon goes through the slit, that photon should go in a straight line and hit here. And let's say another photon goes through this slit, it should go in a straight line and hit there. But that's not what happens. If we have our double slit, and there's our photodetector, let's shoot a single photon. We expect it to go through one slit and go in a straight line, but it could land almost anywhere. It could land here or here, even in places that are blocked by the wall. How can this be? But if we keep sending photons there, we find that we get a pattern. Photon after photon, some go here, some go here, some go here, some go here, maybe here, but we find a concentration here, 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 and here. We get that interference pattern again. After photon, collectively, they follow that interference pattern. Even though only one goes through, it seems to go to a random direction, but once again, we get that interference pattern. So it appears that a single photon goes through both holes in the slit, interferes with itself, and causes it to go some random direction. So what is going on here? Well, let's take a look at the nature of light. Light is a quantum object, and a quantum object is something that acts like a wave, but what is it? It's a wave of quantum probabilities. So if we take the double slit away and send our beam of light, that means that when the light strikes the wall of detectors, there's a small chance that it will interact with any of these detectors. So here comes our single photon, and it acts like a wave. This is one photon, and it's a broad wave. How can that be? Well, that's the nature of quantum objects. So here comes our photon as a wave, but when it hits our wall of detectors, there's only a tiny chance that it will interact with any one of them, and let's say it interacts with one right here. Once it's interacted, there's only enough energy for one interaction, so it can't interact anywhere else. So although the photon comes as a broad wave, it can only react in one spot. And the wave collapses at the moment of that reaction. So here comes the wave, and then gone, and the reaction is here. Here comes the next photon as a wave. Where is it going to react? Random. Say it reacts there, and then the wave collapses. Can't react anywhere else. So that's the nature of a quantum object. It is a wave, but a wave of quantum probabilities, and it has a certain percentage of chance to react with something. Usually what this is it reacts with an electron and kicks it into a higher energy state, and sometimes that can make the electron move or change the property of a crystal. But anyway, it reacts. Once again, the photon comes as a wave, reacts somewhere, but can only react in that one place. So it comes as a wave, reacts, the wave collapses. It can only be in one place. So this is happening photon after photon, and where it reacts is random. And so after time, we get a random number or equal number of photons anywhere on this detector. If we put the double slit back there, here's the detector, here's our double slit. Well, our photon comes, and what does it do? It's a wave of quantum probabilities. And it goes through here, and it goes through both slits. And we get that interference pattern. So that interference pattern is the interference in probabilities. So it concentrates the probabilities along the lines of this interference pattern. And so we'll get more reactions here, and more reactions here, more reactions here, more reactions here on that interference pattern, and less reactions in between. So one photon comes through, and it reacts randomly with these detectors, but that quantum wave, those quantum probabilities cause those reactions to concentrate along the lines of the interference pattern. Now in these videos that you see on the double slit experiment, they will say, well, the experimenters decided to watch at one of these slits to see where the photon goes through. And just by merely watching, the whole thing collapsed. Well, that's where the problem is, because how do you watch a photon? You can't. If I watch a baseball, well, how do I watch it? Light hits the baseball, scatters off, some of that light hits my eye, and I detect it with photon detectors in the retina of my eye. You can detect photons with cones or rods in an eye, p-n junctions and diodes, or silver iodide crystals on photographic film, but you can't watch an electron itself. So what do they mean if they say they watched a photon? Well, what they mean is that they took the double slit and they put a photon detector right here, p-n junction, whatever. And when the wave came, it always reacted with this detector. Now what happens when that wave hits the detector? It collapses, because as soon as the photon is detected, that quantum wave disappears. And so they put the detector here, and it always goes through that slit every time, and only through that slit. But if they put a photon detector here, it appears to always go through this slit. What happens if they put a photon detector at each slit? Well, now it's random. Half the time it reacts with this one, half the time it reacts with that one. But either way, as soon as it reacts, that quantum object collapses and no longer exists. So if you try to put a photon detector at each of these holes to see where the photon goes through, of course it goes through where you put the detector, because it hits that detector first and it collapses and can go no more, and can't react with itself or interfere with itself anymore. So once we take these two photon detectors away and allow the quantum wave to go through the double slit without interference, or without blocking it, it goes through, interferes with itself, causes that interference pattern of the quantum probabilities, and then causes that pattern on the back of the wall, or where the photon detectors are. So that's the missing link in these videos on how the double slit experiment works and what the nature of light is. So light acts like a wave because it is a wave. It's a quantum object that has a wave of quantum probabilities, and it has a broad front. So it's not a little concentrated object, it's a broad front of a wave. But when it reacts, it only reacts in one tiny area, and so the appearance is that it was something that had a packet of energy that moved in a straight line. Of course, when it goes through one of these slits, it appears to curve because of the interference pattern of the quantum probabilities. So the wave-particle duality of light is simply because of the nature of light being a quantum object, which is a wave, but as we observe it as a wave. We see that it goes through a double slit, it interferes, it acts like a wave. but when it reacts with something, it appears to have been an object that went in a straight line or was manipulated by this interference here, but it appears to be an object that goes in a straight line, originates in one place, travels to another, and causes something to happen. So that is why photons have a wave-particle duality, because of the nature of quantum physics and quantum particles. And you'll find that other objects act the same way. They can do the same experiment with electrons. In fact, one of the videos I have linked does the experiment with electrons instead of photons, but it works the same way.